Hello friends, welcome back. In our previous lecture we are discussing about center of pressure, aerodynamic center and the relationship between them, and we also witnessed how CL varies with angle of attack and how can we model mathematically CL variation with alpha, right. So we had CL is equals to CL naught plus CL alpha into alpha. This corresponds to variation of lift coefficient with angle of attack in the linear regime of angle of attack, right. So at the same time we have defined two important parameters, right. One is aerodynamic center, the other one is center of pressure. So center of pressure is a point about which resultant aerodynamic forces act, right. And aerodynamic center, so about center of pressure the pitching moment is 0, right, XCP, and aerodynamic center is defined as the point about which pitching moment remains constant with angle of attack, right. So let us now consider an aerofoil and say XAC is the distance of aerodynamic center with respect to the leading edge, and XCP is the length of this center of pressure, right, the location of center of pressure with respect to leading edge here, right. Now let us take the moment, let O be the leading edge here, and we are going to write a moment, we are going to derive the moment expression about this point O for this particular aerofoil, right. Say we are testing it at certain alpha, right. So let us consider this, there is a flow with a velocity V infinity over this aerofoil. Now the pitching moment about point O is equals to, so when there is a flow there is lift here and drag, and there is lift and drag and moment about aerodynamic center, right. Now let us consider the moment about point O by considering the aerodynamic center here, by considering the forces and moments acting at aerodynamic center. So moment about aerodynamic center minus x aerodynamic center into lift, this equals to Cm is equals to Cm AC minus x bar AC into CL, where M is equals to half rho V square S C bar into Cm, and L is equals to half rho V square S into CL, and x bar AC is equals to XAC divided by C bar, right. Now if you take the moment about the same reference point but by considering the forces acting at the center of pressure, so what we have is the moment due to, since center of pressure is defined as the point about which the resultant aerodynamic forces act, right. So the moment that, so we are considering only the moment contribution from lift because the this is along the same axis, the drag contribution is very less here, so we are neglecting drag here, and so due to lift we have a pitch down moment here, so XCP momentum multiplied by, since it's a non-dimensional coefficient, you will also have C bar into CL, which is equals to minus x bar Cp into CL. So these two equations represent the moment about point O due to lift, right. So the moment should be equal, whether Either you are considering with respect to aerodynamic center or center of pressure. Right? By equating those two, what we have, x bar AC or x bar CP is equals to x bar AC minus Cm AC divided by CL. So this is the relationship between center of pressure and aerodynamic center. We also address that at higher angles of attack, the CL increases, right, due to which this quantity becomes very low, and this x center of pressure will move close towards aerodynamic center. Now let us take a small example. So let us take up an example. A NACA 2412 airfoil is tested in a low speed wind tunnel. It is observed that the pitching moment coefficient about the leading edge at 0 lift is minus 0.02. Also at alpha is equal to 8 degrees, the CL is measured to be 0.7 and Cm about leading edge is minus 0.2. Now we have to find the aerodynamic center for this airfoil, right? Now given Cm about leading edge at CL is equals to 0 is minus 0.02, right. So we know from this equation, so moment about leading edge, say here, is Cm AC, CL is 0, right, it is mentioned CL is 0 and the moment measured to be minus 0.02, which turns out to be the moment about aerodynamic center, right. Let us say this is our leading edge and this is my aerodynamic center. Let this distance be x AC. So V infinity and alpha will have lift and moment about aerodynamic center. Now if I write an equation for pitching moment about aerodynamic center, right, about this leading edge with respect to this aerodynamic center, what we have is Cm is equals to Cm about leading edge is equals to Cm about aerodynamic center minus x bar AC into CL, right. So it is mentioned here that at CL is 0, the Cm is measured to be minus 0.02. That means the Cm AC is minus 0.02. This implies Cm AC is equals to minus 0.02, right. And another information we have here is at alpha is equals to 8 degrees, right, CL is equals to 0.7 and Cm is equals to Cm at about leading edge is equals to minus 0.2. So from the same equation we have CL and at alpha 8 degrees we have CL and the corresponding Cm, right. Can we substitute these two? Minus 0.2 is equals to Cm AC is minus 0.02 minus x AC, x bar AC into what is CL? 0.7. X bar AC is equals to minus 0.02 plus 0.2 divided by 0.7, right, it is 0.2571. So x bar AC is 0.2571. X bar is a non-dimensional number, right. So what we have is x AC is equals to 0.2571 of C bar, right. This equals to 25% of C bar, right, or almost quarter chord of this C bar, right. So the aerodynamic center in general lies for a low speed flight vehicles, the aerodynamic center in general lies at about 22 to 26% of mean aerodynamic curve, C bar, right? And also it is worth noting that the center of pressure keep varying with angle of attack. Why? You have CL keep changing here from this equation. At the same time, you know, as the angle of attack changes, the pressure distribution changes, right? And once you have different pressure distribution, you have different centroid further distribution. So XCP keeps varying, whereas XAC remains constant for over a range of velocities. And of course, angle of attack, it always remains constant, right? So till now we are talking about airfoils. Let us say if I extrude this aerofoil, what you have is wing, right? So aerofoil is also known as infinite wing or two-dimensional wing, right? So this is a 3D object, whereas airfoil is 2D, right? Or also termed as infinite wing. Okay. Now, since it's a 3D object, it is worth talking about its planform geometry. So let us talk about wing geometry. Assume that this is an aircraft, okay? So we have a wing here and we have a horizontal stabilizer, right? Now what in general we assume is this wing extends till the center line of this. Let us say this is my center line or fuselage reference line, right? So wing extend till the center line. Right. Now, when you are measuring the planform geometry, planform is the top view of this, right? Top view of the wing. When you are measuring the planform geometry, that means if you want to check the length of this wing, which we call here is as span, right? Span is a lateral length of this wing, right? This is a lateral direction. This is span, which is the length measured from tip to tip. You call this as tip of the wing, you call this as root, right? Now let me just erase the fuselage. Okay, so this, what you have here is the root, and the longitudinal length of this aerofoil will be say what is longitudinal length? Length in this direction, right? So what will be the longitudinal length? Is it nothing but the cross-sectional length at that particular point? So what do you have at this cross-section is an aerofoil. So you measure aerofoil in terms of chord. The longitudinal length of this aerofoil is chord. So the longitudinal length of wing also at that particular location is a chord, right? So the one that is present at the root is known as root chord. And at the tip we have tip chord. So let us consider CT be the tip chord and CR be the root chord, right? And you have a span, right, which is the distance length between the length measured between tip and tip to tip of this wing, right? At the same time, you have area here, area of the wing. Let S be the area of the wing, B be the span, CR is the root chord, CT be the tip chord, right? Now let us talk about some of the non-dimensional parameters here of the wing. We define something called aspect ratio, which is B square by S, right? There is no dimension for this. And for a delta wing configurations, right? So this aspect ratio will be usually will be less than 3 or 4 or 5, let us say. We call them as low aspect ratio wings. And a sail plane from 8 to 16, and for a glider it will be beyond 16, right? And aspect ratio is B square by S here, and taper ratio lambda. Let us denote taper ratio as lambda. This is aspect ratio, lambda is taper ratio. See, what are we tapering? We are tapering the chord. When you are reducing the chord, we witness that the maximum thickness and everything will reduce, right? You are scaling down, in fact, right? You will be reducing the chord length here. When you say taper, you are trying to reduce the chord length as we move along the span of this wing. So taper ratio lambda is CT by CR, right? When we mention taper ratio, are we missing anything? Do we need some other information? Do we require any additional information? Or when we talk about a taper, is this lambda sufficient enough? Or do we require any other information? So as far as I am concerned, see, let us consider this pointer, right? So you see the radius is, it is conical in shape, right? And the diameter here is large compared to that of tip. Yeah, definitely, because you have for a cone, you have a bigger base and a smaller tip, right? Now, you see it has been, the diameter has been reduced, but the reduction has happened about a particular axis, right? It is for this particular stick, for this particular pointer, it happened about the longitudinal axis, right? Longitudinal axis of this pointer. But for a wing, what are the possibilities? So if you look at here, what you can see is it is tapered about trailing edge, right? That means your trailing edge of each and every aerofoil are in the same location, right? Or in the same straight line here. They are tapered. It is, so the wing is tapered about trailing edge. Okay. So what you require is axis for taper, axis about which this taper, you are tapering the wing, right? Axis for taper. Yeah. And now let us consider a classical or a rectangular wing. So what do you mean by rectangular wing? At each and every point you have equal chord, right? So let this be C, right? So what will be the aspect ratio of a rectangular wing? For a rectangular wing, aspect ratio is equals to B square by S is equals to B square by B into C, B by C. B by C is the aspect ratio. So what will be the taper ratio? Lambda here is CT and CR are same. So CT by CR is equals to 1. So let us consider another case. Is a triangular wing or a delta wing, right? So what is the tip chord in this case? This is CR. What is CT? Is 0. For a delta wing or a pure or a triangular wing, we have lambda is equals to 0, right? So the lambda varies from 0 to 1, right? Okay. Now we have this rectangular wing. Okay. Let us assume about some point we are trying to rotate this wing. Understand? Rotate this two halves. About this point we are trying to rotate, give a rotation. So initially, say you have a rectangular wing, right? So about this point you are trying to rotate this wing. What happens? Am I correct? It almost looks like this, right? What you have done is you have rotated by an angle about some reference point, right? If you take this rotation about leading edge, or in general, this angle is known as sweep back angle or swept. Wing is swept, sweep angle. So if you sweep it forward, it is sweep forward, and if you push it, if you rotate the wings backward, then it is sweep back angle, right? Capital omega. So this is the leading edge, you have leading edge sweep, and if you sweep about trailing edge, you will have trailing edge sweep. About quarter chord, you will have quarter chord sweep. Similarly, taper you will have it about quarter chord taper or mid chord taper or trailing edge taper. Like the aerofoils here will be, say if this is my V infinity, the aerofoils will be, the chord of this aerofoils will be aligned with the flow. But right now what happens is a component, so if this is V infinity, then whatever the aerofoils will face is a phase that generates lift is V infinity cos omega, right? So usually swept is essential when you are traveling at high speeds, right, to delay the Mach number on the airfoil, right? Although with respect to ground you will be traveling at a higher Mach number, but the aerofoil sees a lower Mach number, right? That we will discuss as we progress. And this is a sweep, right? At the same time, when there is sweep, there can also be a taper, right? It doesn't mean that only sweep, only rectangular wings are swept. You can also sweep the tapered wings. We also have something called dihedral, right? Okay. So let us say this is your actual wings level attitude. This is the front view, right? You have propeller here mounted on the nose. This is a front view, right? Now let us say this is my wings level attitude. So the angle made by the wings with this level attitude is known as dihedral. So we will see why we need sweep and what is dihedral, why we require. Right? What are the conditions during which you have to use the dihedral for a wing? Okay. Now coming back to this planform geometry. So say this is your root chord. Okay. Now so this is your wing. Say if the aerofoil here, so the aerofoil here, say the same aerofoil we are using, if it is rotated with respect to this root chord, okay. So the aerofoil which is present at this particular section is rotated with respect to this. If the wing has aerofoils which are with different orientation, right, you can have a constant twist or a variable twist wing, right. So as you progress along the span of this wing, you can actually orient aerofoils at different angles, right? What we call that as twist. So you call this as twist, which is by geometry, right? You are not changing the aerofoil, you are using the same aerofoil and you are rotating it. You call it as geometric twist. Okay. So let us say I am not giving any physical twist, but say if I change aerofoil, right, at the root chord I will be using one aerofoil, and as I progress along the span I will be changing the aerofoil itself. Although I am not giving any twist, but the shape that once you look at the shape, right, because when you change the aerofoil, the upper surface and lower surface coordinates changes, right. With respect to root chord, it will be of different thickness and all. So that gives you a aerodynamic twist. You are changing the aerodynamic characteristics of the wing as you progress along the span. So this is geometric twist. So aerodynamic twist is like you use, here I may use a symmetric aerofoil, right, and here I may use symmetric aerofoil or another type of aerofoil with different thickness, right. So ultimately you are changing the aerodynamic, by changing this aerofoil you are actually changing the aerodynamics along the span. So this particular twist, although it is not a physical twist, but from the geometry it looks as if the wing is twisted. So this particular twist is known as aerodynamic twist. Right. So as far as the wing is concerned, if you slice it, right, at different locations, what you have is an aerofoil. The structural name for this particular aerofoil is a rib, right. So you will have ribs and you will have spars that connect these ribs, and to cover this skeleton, this forms the skeleton of the wing, and to cover this skeleton we will have skin, right. So instead of making a solid wing, we'll be trying, the whole idea is to design a wing which can have equal strength or sufficient strength, right, by making it as hollow as possible. So let us look at one of the wings of a UAV that we are going to develop. Yes friends, what you are looking at is a 4-meter span wing that we are going to develop for a UAV, right. It's a scaled down wing. So the actual scale turns out to be 16 meters around the span of the actual scale, right. So you can see at different locations we have ribs here, right. I'll request one of my researcher to come here to help me out. Mr. Himanshu, can you please help me? Yeah. If you can hold, I can explain better, I guess, right. So it's a twin boom UAV where the tail, horizontal tail, will ultimately end up landing resting on these 2 booms, right, which are extending from the wing. And what you have here is ribs, right, and at most of the places we have removed the material to optimize the weight. And you have spars here, so these are the carbon fiber tubes that you can see here, and at some places we have also covered with the skin, right. So this is the covered part of it, you can see. So and yeah, it is tapered, right. You can see that the wing is tapered. See the taper, right. So you can see the thickness also reduces along the span. I thought this will be a bit interesting for you, so I got it in between the fabrication, right. I stopped them, so you can give it back to them, right. Okay. So coming back to the planform geometry, now as we can see from the root to tip the chord is varying, but in all the moments and while considering the moments we are considering some reference length, right. In case of pitching moment we are considering it as the chord, right, for an aerofoil. But what happens, which length we need to consider for a wing when it is getting tapered, right. When I mean tapered, the chord is varying, the length of the chord is varying along the span. Now there is something called mean aerodynamic chord, right. MAC. C bar, right. So what is this mean aerodynamic chord? Instead of this entire wing, I can represent this wing by means of a straight line for the purpose of analysis, right. So let us say if I want to replace this entire wing, right, all I can represent this by means of a straight line, which is C bar of the wing. Okay. And why? Because to represent what ultimately we have to represent the wing in terms of lift, drag and moment, right. So this, and we witnessed that we represented lift, drag and pitching moment about the aerodynamic center. Similarly, if I know the chord and the corresponding aerodynamic center, right, that is good enough for me to represent the entire wing. Okay. Now let us see how to find the mean aerodynamic chord as well as the aerodynamic center of this wing. Right. So the units are meters here, right, general units are meters. So you have root chord and you have tip chord. So let us say CR or C bar or the mean aerodynamic chord is given by 2/3 CR into 1 plus lambda square divided by 1 plus lambda, where lambda is equals to CT by CR, right. So this is like, once you do that, then you will end up getting a mean aerodynamic chord on either side, which is symmetric in case of a fixed wing aircraft, right. Now what you have to do is project this mean aerodynamic chord onto the root, right, onto the root chord or the fuselage reference line or the center line here, right. So and we witness that like this, the aerodynamic center lies at the 25% of this C bar, mean aerodynamic chord, right. So now for a rectangular wing, let us say, what is C bar is equals to C or C root, right? So what is lambda? So 1 2 by 3 into CR into 3 by 2. This becomes, for rectangular wing, C bar is equals to CR is equals to CT, right? You can verify this from this equation. And where, so what is the distance for this, what is the distance at which this C bar is located, right, or span wise distance? So y of MAC. So if I want to know what is the y location or the span wise location of this C bar, we have y MAC is a span wise location of mean aerodynamic chord is b by 6 into 1 plus 2 lambda by 1 plus lambda. So with the help of these equations, we will be able to find the C bar of a given wing, and 25% of this C bar is a aerodynamic center. So how to find aerodynamic center of wing? It's like 25% of MAC, mean aerodynamic chord, measured from leading edge. Measured from leading edge of C bar. Find the aerodynamic center of the following UAVs, right? So in the first place, let us consider a pure delta wing. Let this be, span be 2 meters and root chord be 1 meter, right? So how to find the mean aerodynamic chord? This is, let us say this is my mean aerodynamic chord. So C bar is given by 2/3 CR into 1 plus lambda square by 1 plus lambda. What happens? What is CR? 1 meter into what is lambda? Lambda for this delta wing is 0 by 1, right? CT by CR, that is 1, right? So 2 by 3 is how much? 0.67 meters. So 0.67 meters is your mean aerodynamic chord, right? So what exactly a delta wing is here? For a low speed, assuming that there is no actual sweep here, so it is actually a tapered about trailing edge. The wing tapered about the trailing edge. So generally, to construct this, what happens? Usually if there is a sweep, right, you will take a component of this, you will project the aerofoil along the flow, and you will take that aerofoil as a rib to construct your wing. Okay. So, but in this case, but the low speed flows that we are talking, we are not going to give any sweep, right? Consider, so you can consider in this course this delta wing whenever we discuss, it can be a wing tapered about the trailing edge, right? in most of the cases. Otherwise, if I otherwise mentioned, it is like tapered about trailing edge. Yeah. Now, since it is tapered about trailing edge, what I can do? I can project directly because the trailing edge remains same. So this becomes my C bar. So 25% of the C bar is, so MAC, like aerodynamic center, is equals to 1/4 of C bar is equals to 0.67 by 4.16. So this aerodynamic center that we got is with respect to the leading edge here, which is located at a distance of 0.167 meters, right? And what is this distance? CR minus C bar, right? So let us say if this is my XAC, aerodynamic center, right? So XAC is equals to CR minus C bar. CR minus C bar will give you this length and plus 25% of C bar, that is 0.25 C bar, right? So what you get here is 67 is, and from 1 meter it is like 33 centimeters plus 16 centimeters, 49.7 centimeters or approximately 0.5 meters. So the aerodynamic center lies at a distance of 0.5 meters from the nose of this delta wing.